All right, in just the next few minutes, we're going to pull back the curtain on the hidden language that powers, well, pretty much everything: the electric circuit. It's this invisible force, right? But it follows some super simple, elegant rules that, once you get them, explain almost all the technology that surrounds us. Let's dive in. You know, Francis Bacon really nailed it with this quote. Some topics you can just skim, but when it comes to electric circuits, that's exactly what we're going to do. We're going to chew on this thing, digest it, and really break it down so you can truly get a handle on it for good. Okay, just look at this thing, NASA's Mars rover. It's an absolutely incredible piece of engineering, doing its job millions of miles away in space, where you can't exactly call a repairman. But here's the really mind-blowing part. This ridiculously complex machine runs on the exact same basic principles we're about to cover. And those same roles, you're about to understand them. And hey, it's not just rovers on Mars, right? Those exact same principles are humming away right now in the device you're watching this on, in the lights overhead, and in the giant power grid that connects all of our cities. From the most amazing feats of engineering to the simplest tools we use every day, circuits are the thing that ties them all together. Okay, so what is a circuit, really? When you boil it all down, it's just this: a closed path made of different electrical parts all connected up. And its job is always one of two things: either to move energy, like turning on a light, or to move information, like sending a signal for your Wi-Fi. That's literally it. It's a road for electricity to travel on so it can do some work. All right, to really get what's going on with that pathway, we've got to zoom in. I mean, way in. We're talking about going down to the atomic level to meet the real star of the show, the tiny little particle that makes this whole thing possible: electric charge. So, charge is just a fundamental property of matter, kind of like mass is. It's the thing that makes particles like electrons and protons notice each other and interact. We measure it in something called coulombs. All you really need to remember is that electrons have a negative charge and protons have a positive charge. Simple. And just to give you a sense of the scale we're dealing with here, get a load of this number. That is the insane number of electrons you'd have to round up just to get one single coulomb of charge. What that tells you is that the charge on one single electron is just unimaginably tiny. Okay, so we've got all these zillions of charged particles hanging around, but just sitting there, they don't really do much for us. The real magic kicks in when we can get them to move in an organized way, and that movement, that flow of charge, that's what we call current. The best way to think about it is like water flowing through a hose. The water itself is like the charge, but the current is how much water is flowing past a certain spot every second. In the world of electricity, we measure this flow in amps, or amps. So it's not just about the charge moving, it's all about how much is flowing past a certain spot in a specific amount of time. Okay, now here's a kind of weird but super important history lesson we got to get straight. See, way back in the day, Benjamin Franklin took a guess and said electricity was a flow of positive stuff. Turns out he got it backwards. It's actually the negative electrons that do the moving in a wire. But hey, the idea stuck, so to this day, whenever we draw a circuit, we show the current flowing from positive to negative, even though we know the electrons are really hoofing it the other way. Kind of funny, right? So this flow of current really comes in two main flavors. You've got direct current, or DC, which is this nice, steady, one-way street of flow, like the power you get from a battery. Then there's alternating current, or AC. This one is constantly switching directions, flowing back and forth, back and forth. And that's the juice coming out of the wall sockets in your house. All right, so we get it. Charge flows, and that's current. But why? What actually makes it move? It doesn't just decide to get up and go. Well, it needs a push, a kind of electrical pressure. And that's where voltage and power enter the scene. Let's go right back to that water hose analogy, because it's perfect here. If current is how much water is flowing, then voltage is the pressure pushing that water through the hose. It's the force that gets the charge moving. Simple as this: no pressure, no flow. No voltage, no current. We measure this electrical push in volts. And this right here is where it all clicks into place. Because when you have that push, the voltage, and you have the flow, the current, that's when you get power. Power is just the rate that energy is being used. You figure it out by multiplying the voltage times the current, and we measure it in watts. This is literally the wattage you see printed on a light bulb. It's telling you how much energy it's using every second. So let's put it all together. It's really just a simple chain reaction. Check it out. First, the voltage provides that push. That push makes the charge start moving. That moving charge, that is our current. And finally, that push and that flow working together, that's the power that actually gets stuff done. You know, the direction the current is flowing actually tells us a really simple story about who's doing the work. Just think of it like this. If the current is going into the positive terminal of something, like a lamp, that thing is absorbing or using power. But if the current is flowing out of the positive terminal, like in a battery, that thing is supplying the power. It's just a handy way to keep track of what's giving the energy and what's using it. All right, let's zoom back out for a second. We've just covered the big four: charge, current, voltage, and power. And believe it or not, with just those four simple ideas, you now have the fundamental toolkit to understand how basically everything works, from a simple flashlight all the way up to that Mars rover. I mean, look at these two things, a basic flashlight and a complicated radio. On the surface, they seem like they're from different planets, right? But here's the secret. That complex radio is really just a bunch of simple parts all connected together, and every single one of those parts follows the exact same rules as the simple flashlight. It's a perfect example of how, in electronics, incredible complexity is usually just simple ideas repeated over and over again in really clever ways. And honestly, that is the biggest thing I want you to take away from this. Every single electrical gadget you have ever used, no matter how complicated it seems, runs on that same small set of rules. Once you get a handle on them, you really hold the key to understanding the language of our modern world. So there you have it, a few simple ideas that literally built the world we live in, from the phone in your hand to robots on other planets. So the question I'll leave you with is this. Now that you understand these fundamental rules, what's next? What amazing new things do you think they're going to power for us tomorrow?